Look up at the night sky, and you might see a tiny point of light moving across the darkness. It could be a satellite. Somewhere hundreds or even thousands of kilometers above you, it's traveling around Earth at an incredible speed. But there's something strange about that. Gravity is constantly pulling it toward Earth. So why doesn't it fall? It sounds like satellites are somehow floating above the planet, perfectly suspended in space. But that's not what's happening. In fact, a satellite is falling toward Earth right now, and it has been falling the entire time. The reason it doesn't crash is one of the simplest and most fascinating ideas in physics. It's moving sideways so incredibly fast that while gravity pulls it downward, the surface of Earth curves away underneath it. Imagine throwing a ball. If you throw it gently, it travels forward for a moment before gravity pulls it down to the ground. Throw it harder, and it travels farther before hitting the ground. Now imagine you could throw that ball incredibly fast. So fast that while it falls toward the ground, the Earth curves away beneath it. The ball would keep falling, but it would never reach the surface. Instead, it would keep going around the planet. That's an orbit. And this is essentially what a satellite is doing. It's not escaping gravity. It's actually using gravity. Earth's gravity constantly pulls the satellite toward the planet, while the satellite's enormous sideways speed keeps carrying it forward. Those two things work together to create a continuous fall around Earth. But to understand why this works, we need to forget one common idea about orbiting objects. A satellite isn't sitting still above Earth. It's moving incredibly fast. A satellite in low Earth orbit can travel at roughly 28,000 kilometers per hour. At that speed, it can circle the entire planet in roughly 90 minutes. So imagine standing on Earth and watching a satellite pass overhead. It may look like it's simply gliding across the sky, but in reality, it's racing forward at thousands of kilometers per hour. And this speed is exactly what keeps it from hitting the ground. Think back to that ball. Gravity pulls the ball downward, but because you threw it forward, it also travels horizontally. The faster you throw it, the farther it gets before gravity brings it down. On Earth, the ground eventually gets in the way. But Earth isn't flat. It's a giant curved surface. If you could throw the ball fast enough, the ground would keep curving away from the ball as the ball falls. Eventually, the ball would be falling toward Earth at exactly the same time that Earth is curving away from it. The ball would never stop falling. It would simply keep missing the ground. That's an orbit. And this is one of those ideas that sound strange until you visualize what's actually happening. This satellite isn't hovering. It isn't being held up by some invisible force. It isn't outside Earth's gravity. It's constantly being pulled downward. It's just moving forward fast enough to keep missing the planet. But there is a catch. Not every orbit is the same. The farther a satellite is from Earth, the weaker Earth's gravitational pull becomes. That changes how fast the satellite needs to travel to maintain its orbit. Close to Earth, satellites need to move extremely quickly. Higher up, they can orbit at lower speeds. This is why different satellites can take very different amounts of time to go around Earth. Some satellites complete an orbit in less than 2 hours. Others take many hours. And some are positioned so that they take about 1 day to complete an orbit. These satellites are especially useful because their orbital period can match Earth's rotation. From the ground, a satellite in the right orbit can appear to remain above roughly the same part of Earth. This is called a geostationary orbit. It's incredibly useful for things like communications and weather monitoring. But even these satellites aren't actually staying still. They're moving around Earth at enormous speeds. They're just moving in a way that matches the rotation of the planet below them. So now we have the basic idea. Gravity pulls the satellite toward Earth. Its sideways velocity carries it forward. Earth curves away underneath it. And the result is an orbit. But what happens if the satellite slows down? This is where the idea becomes even more interesting. If a satellite loses some of its orbital speed, gravity becomes more dominant. The satellite moves into a lower orbit. If it slows down enough, its path can eventually bring it into the atmosphere. And once that happens, something very important starts working against it. Air resistance. Even though space is extremely empty, low Earth orbit isn't perfectly empty. There are still tiny amounts of atmospheric gas at those altitudes. A satellite moving through the thin atmosphere experiences drag. It's similar to the resistance you feel when moving your hand through water, except the atmosphere at orbital altitude is incredibly thin. That drag slowly removes energy from the satellite's orbit. And this means some satellites actually are falling closer to Earth over time. They don't simply stay in exactly the same orbit forever. Satellites in low Earth orbit can gradually lose altitude because of atmospheric drag. Eventually, without corrections, many of them would descend far enough to re-enter the atmosphere. As they encounter denser air, the effects become much stronger. So satellites sometimes need help staying where they're supposed to be. Spacecraft can use small thrusters to make adjustments to their orbit. These adjustments are called orbital maneuvers. They don't constantly fire their engines to stay in space. Instead, they make occasional corrections when necessary. That's another important misconception. Satellites don't need engines running continuously to orbit Earth. Once they're in the right orbit, gravity does most of the work. The engines are mainly there to change the orbit or correct it. But getting a satellite into that orbit in the first place is a completely different challenge. You can't simply build a satellite, launch it straight upward, and expect it to stay there. If you launched it straight up, gravity would eventually pull it back down. To enter orbit, the spacecraft needs enormous sideways velocity. That's why rockets don't just go straight up. They initially travel upward to get through the thickest part of the atmosphere. Then they gradually tilt and accelerate sideways. The goal isn't simply to get high. The goal is to get high while moving sideways incredibly fast. Eventually, the spacecraft reaches the required orbital speed. Then the engines can shut down, and the satellite continues moving around Earth. This is one of the most counterintuitive parts of spaceflight. A rocket needs its engines to accelerate the satellite into orbit. But once the satellite is in orbit, it doesn't need to keep accelerating just to continue moving. There's almost nothing in space to slow it down. So the satellite keeps moving because of its momentum. Gravity continually bends its path. Instead of flying away in a straight line, its trajectory curves around Earth. And that's how you get in orbit. But there's an even bigger question. If gravity is what keeps satellites in orbit, why doesn't gravity eventually pull every satellite straight into Earth? The answer is that gravity isn't simply pulling an object downward. It's constantly changing the direction of the object's motion. Imagine throwing a ball. At the instant you release it, the ball is moving forward. Gravity immediately starts changing its trajectory downward. If you could remove the Earth from the equation, the ball would continue moving in a straight line. Gravity bends that straight path. For a satellite, the same thing happens on a much larger scale. Its natural motion would carry it forward in a straight line. Earth's gravity continuously bends that path inward. The result is a curved trajectory around the planet. So an orbit is really a balance between motion and gravity. Not a perfect balance where nothing happens. A constant interaction where something is always happening. The satellite is moving forward. Gravity is pulling inward. And the path keeps curving. That's why the phrase falling around Earth is actually a surprisingly accurate way to think about orbit. The satellite is falling. It's just falling around the planet instead of directly into it. And this isn't unique to artificial satellites. The moon is doing essentially the same thing. The moon is constantly being pulled toward Earth by gravity. At the same time, it has enough sideways motion to keep missing Earth. Earth itself is also orbiting the Sun in the same basic way. The Sun's gravity pulls Earth inward, while Earth's motion carries it forward. So when you look at a satellite moving across the night sky, you're watching the same fundamental physics that governs the motion of planets and moons. There's nothing magical holding it up. It's gravity and motion. And this idea becomes even more impressive when you realize how precisely engineers can control it. A satellite's orbit can be calculated using its position, speed, altitude, and the gravitational forces acting on it. Scientists can predict where it will be. They can determine how much it will move over time. And when necessary, they can make small adjustments to keep it on the correct path. Some satellites are designed to observe Earth, Some provide communications. Some help with navigation. Some monitor weather. And others study the universe itself. All of them depend on the same basic principle. They are falling around Earth. So the next time you see a satellite moving across the night sky, don't imagine it as an object simply floating above the planet. Imagine something moving at thousands of kilometers per hour, constantly being pulled toward Earth by gravity. It doesn't stay up because gravity stopped affecting it. It stays up because it's moving so fast that as it falls, the Earth keeps curving away beneath it. And that means the strange truth about satellites is actually very simple. They don't stay in space because they aren't falling. They stay in space because they are falling constantly. And they keep missing the Earth.